Oh, good morning, everybody. Hope you had a good Thanksgiving. This is lesson 25 on Riemann sums and integration. So we have 4 more classes, including today. 3 are on topics on integration. And then the last class is always the review for the final. The review sheet for the final will be a practice exam from a previous year. And if you don't already have it, then I will post it on Blackboard pretty soon and send it out to you. Are there any questions before we start? Everybody hear me? Anybody hear me?
I got you. So when is the final exam? On the 14th?
Whatever day I emailed to everybody. I sent out an email with the final exam date. I posted it on Blackboard, and I take it exactly from the final exam schedule for Lehman. So whatever it says, I just don't remember, but I emailed it to you. And it's on Blackboard.
Okay.
Okay. Final exam is different from the midterms. The final exam is made up by the department. It's a departmental exam. So it has more questions, a lot more questions, but they don't have multiple parts. So in any case, that's what you'll see what the final exam is if you haven't already looked at the practice exam that's on the department website. All right, so we've already studied what is called the indefinite integral, which is a fancy word for the antiderivative. So if we have a function f of x, the indefinite integral, which is denoted like this, is some other function, capital F of x. And so this capital F of x is the integral if the derivative, df dx, is little f. So for example, if we want to find the indefinite integral of the cosine of x dx, what is that? Well, that is the sine of x. Because if you differentiate the sine, you get the cosine. The indefinite integral of 1 over x dx is log x, because the derivative of log x is equal to 1 over x. The integral of 1 over 1 plus x squared dx is the arctangent of x, because the derivative of the arctangent is 1 over 1 plus x squared. So this is what we studied before the break for Thanksgiving. Now, I want to today look at a different problem, which is the problem of finding an area. So you know from elementary school that if you have a triangle, and this is the base, and this is the height, the area is a half the base times the height. And if you have a rectangle, and this is the base and this is the height, the area is the base times the height. And if you have a trapezoid, this is the height, this is the base on the bottom, this is the base on the top, the area is the height times the average of the base on the bottom plus the base on the top, right? So these should be familiar from wherever you learned about some geometry. You have a parallelogram. Again, if this is the base and this is the height, the area is the base times the height. If you have a circle of radius r, the area is pi r squared. And if you have a sector of a circle, so this is an angle theta measured in radians, the area is 1/2 theta r squared. If you had the whole circle, angle was 2 pi. This is exactly the same as a half, 2 pi r squared. So you see that the formula for the area of a circle is a special case of the area for the formula of a sector of a circle. Yeah. Any questions about this? The only other thing we need to know before we start to talk about areas of more general regions is the following. I mean, here's what we would like to solve. So we want to solve problems like the following. Suppose we take a parabola. Say y = x squared. So this is the point 2,4. Suppose we want to find the area under the parabola. Or suppose we have a more interesting problem. Suppose we have a parabola and a line. So here we have a parabola, and here we have a line. So this is my parabola. This is a line. I want to find the area of the parabola cut out by the line. Okay. So we want to be able to solve problems like this. Or in one more problem, we know the area of a circle. Suppose we have an ellipse. Here's the area in green. What is it? Suppose the ellipse is given by the equation x squared over a squared plus y squared over b squared equals 1. So this is a minus a, b minus b. What is the area? So this is the problem in geometry we want to solve, and the way we solve it is by using some calculus. And the way I'll start is by just recalling what is sometimes called sigma notation. If we have some numbers, say a1 plus a2 plus a3 plus a4 plus a5, and we don't want to write this whole thing down, we use, this is the Greek letter capital sigma. I goes from 1 to 5, a sub I. That's the notation for this. Okay. Or more generally, if you had summation, let's say I goes from 7 to 13, a sub I, this means A7, you go through all the numbers from 7 to 13, A7 plus A8, and so forth, up to A13. So this is what is called sigma notation. And more generally, summation, let's say I goes from 1 up to n, A sub I is the sum of all the elements of this sequence from A1 up to AN. Okay. Questions about that? Okay, now you might remember from, well, actually, let me just give a couple of examples of specific uses of sigma notation. Suppose we have a number C, and if we write C, summation C, I goes from 1 up to n, every term of the sequence is C. This means C plus C plus C up to C n times. That's n times C. Someone's asking about the final. It's not multiple choice, it's a regular exam. You write out the answers to the questions and make a PDF file and upload it to Blackboard. It's just instead of a small number of questions with parts, there are a large number of questions without parts. All right. So this is the sigma notation. Suppose we have summation I goes from 1 to n I. This means when I equals 1, it's 1. When I equals 2, it's 2. So this means the sum of the first n positive integers. And there's a simple formula for this, which you can see as follows. If you take the first term and the last term, and you add them up, you get n plus 1. If you take the second term and the next to the last term, and you add them up, n minus 1 plus 2 is also n plus 1. If you take the third term and the third from the last term, n minus 2 plus 3 is n plus 1. And you see if you pair these off, like an onion, this coming in from the ends, you have pairs of numbers that add up to n plus 1. And if you have n numbers, how many pairs are there? N over 2. So we have this formula, which you need to know, for the sum of the first n integers. It's n times n plus 1 over 2. And there are also formulas for the sum of the first n squares. This is 1 plus 2 squared plus 3 squared up to n squared. That's 1 plus 4 plus 9 up to n squared. And this is n times n plus 1 times 2n plus 1 over 6. It's important to see this at some point. You're not going to have to memorize them, but it's important to have seen them because we're going to use them. If you take the sum of the first n cubes, so that's 1 plus 8 plus 27 up to n cubed, that has a very pretty formula. It's n squared, n plus 1 squared over 4. In fact, this is exactly n times n plus 1 over 2, all squared. Here's n times n plus 1 over 2. This means this is summation I goes from 1 to n, I, all squared. So we have this curious fact. If you take the sum of the first n integers and square it, you get the sum of the first n cubes. So that's really very pretty. Now, why is that useful? Well, it's useful because we want to solve the problem of calculating an area. So let's start with the first example in the text. We have f of x equal minus x squared plus 5. So this is a parabola. When x is 0, it has the value 5. When x is 1 or minus 1, it has the value 4. When x is 2 or minus 2, it has 5 minus 4, it has the value 1. When x is 3 or negative 3, 5 minus 9 is minus 4. So this parabola looks something like this. And we want to find the area under the parabola from x equals 0 to x equals 2. Well, this is the vertical line, x equals 0. This is the vertical line, x equals 2. And we want to find this area. So this little bit right here doesn't count. It's to the right of the line too. Draw a cleaner line maybe so it's easier to see. So our parabola comes down like that. And we want all this part. So that's a hard problem. And the way we deal with it is to start by saying, well, let's approximate this area by figures whose area we know. And the simplest is a rectangle. Rectangle has area base times height. So let me blow this picture up a little bit. Not to scale, but this is 0, 2. Our parabola looks like this. And let's say we take this interval from 0 to 2 and we divide it up into 5, let's say 5 pieces of equal width. So each width is 2/5. This is 2/5, 4/5, 6/5, 8/5, and 2, which is 10/5. So I have these subintervals. Right, I've taken the interval from 0 to 2 and divided it into 5 pieces. And on each of these pieces, I draw a vertical line and I form the rectangle. So I want to form a rectangle where the base is, there are 5 bases because there are 5 rectangles. Each is this interval of length 2/5. And let me take the right-hand endpoint of each interval to build a rectangle. So here I have a rectangle. I have all these different rectangles. And what we can say is the area under the parabola from x equals 0 to x equals 2 is approximately the sum of the areas of the 5 rectangles. The actual area is a little bit bigger, but an approximation is the sum of the areas of these rectangles is less than the total area under the curve, but it's approximately the area. And for each of these rectangles, you see we have the function f of x equals minus x squared plus 5. So what is the area? Let's call this 1, 2, 3, 4, 5. So the area of rectangle 1 is the base times the height. The height, well, it's just the value of the function at 2/5. F of 2/5 times the base. So this is the height times the base. The area of the second rectangle, the height is the value of the function, because right again, this is f of x equals minus x squared plus 5. It's the height is f at 4/5 times the base. For the third rectangle, the height is f of 6/5 times the base. For the fourth rectangle, the height is f at 8/5 times the base. And for the fifth rectangle, the height is the value of the function at 2 times the base. So these are just 5 numbers that we can calculate. And in fact, if you do the calculation, we get, well, I mean, it's in the book, 162 over 25, which is 6.48. So what we can say is that for this curve, y equals minus x squared plus 5, from 0 to 2, the area is bigger than 6.48, because when we added up the areas of these 5 rectangles, which were under the curve, we got 6.48. Now, we can also get an upper bound for the area as follows. Again, let's divide this interval into 5 pieces of equal width, 2/5, 4/5, 6/5, 8/5, 2. And again, we draw these vertical lines. And now I want to form rectangles where instead of using the right-hand endpoint of the interval to construct the rectangle, we use the left-hand endpoint. So the left-hand endpoint here is here. On this interval, this is the left-hand endpoint, and so forth. So now I've constructed these 5 rectangles, and what we can say is that the area under the parabola is less than the sum of the area of the 5 rectangles. And we can add it up. You can see the calculation in the textbook. It adds up to exactly 202 over 25, which is 8.08. So this area is strictly less than the sum of the areas of these 5 rectangles. That's 8.08. So we didn't get an exact value for the area under the curve, but we did find upper and lower bounds for it. We could approximate the area by dividing this interval up into 5 rectangles. And you can imagine if we use more rectangles and more, well, if we use more rectangles, we get an even better approximation to the area. I mean, suppose we use 10. So now we have a picture that looks like this. And you can imagine, you can see actually visually that if you use 10 rectangles and using the left-hand endpoints in this case, we get the 10 rectangles include the area under the curve, but it's a better approximation. And you can imagine that the more rectangles you pick, the more points you divide the interval from 0 to 2 into, you get better and better upper and lower bounds for the area. And the idea is that if you let the number of rectangles increase without limit, go to infinity, then the areas you get, the approximations, should actually converge. And the number they converge to is exactly what we understand and call the area under the curve. So the general notation for this is the following, or let's say a general way to put this all together. Suppose we have a curve y equals f of x. And the curve looks like that. This is the graph from A to B. What we're going to do is to divide the interval divide the interval, the closed interval, written like this, which just means all x between A and B, into some number n subintervals. And it's not necessary to do this, but it makes it simpler. N subintervals of equal length. So if this is the interval from A to B, and we divide it into intervals of all the same width, what is the width? Well, the length will be, well, from A to B, that distance is B minus A. And if you divide it by n, that's going to be the width of each of these little intervals, B minus A over n. And our shorthand notation for that is delta x. So delta is a capital This is the capital Greek letter delta. So in mathematics, we don't have enough letters in the Latin alphabet, which is the English alphabet, if you like. So we had to use a lot of Greek letters. So we have each of these subintervals on length delta. So here's a subinterval. And one simple way to describe what to do is so let's say this is x sub I minus 1, and this is x sub I. Those are the endpoints of the interval. And the distance between them, xi minus 1, is what we call delta x. And let m sub I be the minimum value of f of x in the interval from xi minus 1 to xi. And let capital M sub I be the maximum value of f of x in that same interval. So excuse me one second. Oh, sorry. Okay. Mi is the minimum value. Capital Mi is the maximum value on the interval. So if you form the rectangle whose height is the minimum value, it looks like this. And in this interval, the area of the rectangle is less than the area under the curve. If you take the maximum value on the interval, the area of the rectangle looks like that. And it's bigger than the area under the curve. So the area under the curve for x between xi and x sub I minus 1 is what? Let me just call it a sub I. It's less than or equal to the maximum times the width of the interval. For this rectangle, this is the height and this is the base. And it's greater than little mi times the width of the interval. So I've bounded the area under the curve by below by one rectangle and above by another rectangle. And what we see from that is where we have this function, the area that we're looking at is at most the sum I goes from 1 to n, capital M sub I delta x, and greater than or equal to the sum I goes from 1 to n, little m sub I delta x. So this is the important formula, but only if you understand what's going on, right? That's the hard thing. So we have this interval from A to B. We divide it up into n equal pieces of width delta x equal to b minus a over n. M sub I is the minimum value of f of x on the interval from xi minus 1 to xi. Capital Mi is the maximum of f of x on the same interval. And the area is bounded above and below by these two numbers. And these are numbers we can calculate because they're just multiplications. We're just adding up rectangles. So we can approximate the area from above and below by expressions of this form. And these sums, so summation mi delta x, I goes from 1 to m, and is called a lower sum, or it's actually a Riemann sum, after a mathematician named Riemann who developed a lot of this theory. And when we sum over the maximums, this is an upper Riemann sum. And one of the most important facts in calculus is the following. If you take the lower Riemann sum, and you take the limit of this as n goes to infinity, this limit exists. And if you take an upper Riemann sum, and take the limit of that as n goes to infinity, that limit exists. And if f of x is a nice function, let's just say continuous, and non-negative, greater than or equal to 0, on the interval from A to B, then these two limits exist, and they're equal to the area under the curve for a non-negative function. And we can actually generalize this a little bit. Here in each interval, we're choosing the smallest value of the function. Here we're choosing the largest value of the function. Suppose we have, for I going from 1 to n, let c sub I just be any number between xi minus 1 and xi. We can form the sum f of c sub I delta x. I goes from 1 to n. So the picture is, here's xi minus 1 and xi. Let's say our curve looks like that. We can choose any ci between these two numbers and form the rectangle whose height is the value of the function at c sub I. So this is the area of this rectangle, and we add this up for all n. The limit of this, as n goes to infinity, exists, and this is equal to the area. And this kind of sum is not an upper Riemann sum or a lower Riemann sum, it's just a general Riemann sum. This is what is called a Riemann sum. Okay. So there's a lot here to understand and to think about. But let me just say, this is also what is called the definite integral, which is written as the integral sign, f of x dx. If I just write it like this is the antiderivative, the indefinite integral. But if I put a and b here, this is the lower limit of integration. This is called the upper limit of integration. This is the definite integral of f of x for x between a and b. So for a non-negative function that's continuous, the definite integral is geometrically the area under the curve from a to b, and it's defined as the limit of these Riemann sums. So let's actually solve a problem which we couldn't solve before, but using this definition or algorithm for area in terms of sums of areas of rectangles, I think we can do it. So let me start with a parabola. Suppose we take f of x equal x squared for x between 0 and 2. So that's the parabola. And what we want to find is this area, which we couldn't do using any of the formulas for area that you learned in, I don't know, elementary school, middle school, high school, wherever. But now we should be able to do it. So let's divide the interval from 0 to 2 into n subintervals, and they each have length 2 over n. Right? You divide this from 0 to 2 into n pieces, each of them has length 2 divided by n. Let's calculate the lower sum. So if you take the interval, so let's see, 0, 2, we're dividing it up into pieces of equal length. in this interval, let's say xi is 2I over n, and xi minus 1 is 2I minus 1 over n. And in this interval, the function's increasing. So m sub I, which is the minimum value of the function in this interval, is just the value of the function at the left-hand endpoint, f of x sub I minus 1, which is f of 2 times I minus 1 over n. Yeah, that's what it is. So my lower sum is equal to summation I goes from 1 to n, f of 2 times I minus 1 over n times the width of the interval. So this is summation I goes from 1 up to n, 2I minus 1 over n, all squared, because my function is f of x equal x squared, and delta x is 2 over n. Let's see. Now we have to do some algebra. So I have 2 squared times 2 is 8. I have n squared times n is n cubed. Summation, I goes from 1 up to n, I minus 1 squared. Right? I minus 1 squared, 2 squared times 2 is 8, n squared times n is n cubed. As I goes from 1 to n, I minus 1 goes from 0 to n minus 1. This is 8 over n cubed, the sum of I squared from 0 to n minus 1. I can forget the 0 when I is 0, this is 0, so sum from 1 to n minus 1. Oops, sorry, I minus 1 squared. Let's keep going. So my lower sum is equal to 8 over n cubed, summation I goes from 1 to n, I minus 1 squared. That's 8 over n cubed, n minus 1. Summation I goes from 1 to n minus 1. I minus 1 squared is I squared minus 2I plus 1. So I can write this as 3 sums. This is 8 over n cubed times what? Summation I goes from 1 to n minus 1 I squared minus 2 times summation I goes from 1 to n minus 1 I plus summation I goes from 1 to n minus 1, 1. Oops, I'm sorry. I just made a mistake back here. This is the summation I goes from 1 to n, and I want to follow the way the book does it. So I goes from 1 to n, that doesn't change. I goes from 1 to n. I goes from 1 to n. Okay. Now these are sums that I wrote down previously. The sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. The sum of the first n integers is n times n plus 1 over 2. And if you add 1 to itself n times, you get n. So what do we have? Multiply this out. Let me just do it. You get 2n cubed plus 3n squared plus n over 6. These twos cancel. So it's minus n times n plus 1, n squared minus n plus n. And these cancel. And minus n squared is like minus 6n over n squared. So this is 8 over n cubed. 2n cubed minus 3n squared plus n over 6, which is, I can take out the 6. This is 4/3. 2n cubed minus 3n squared plus n over n cubed. This is equal to 4/3. 2 minus 3 over n plus 1 over n squared, which is 8/3 minus 4 over n plus 4 over 3n squared. So we just did this calculation. This is the lower sum. And the limit, as n goes to infinity, of this lower sum, it's the limit, as n goes to infinity, of 8/3 minus 4n plus 4 over 3n squared. These go to 0. That's 8/3. And if we do a similar calculation for the upper sum, we also get 8/3. So we just proved the following remarkable geometrical fact. If you take the parabola y equal x squared from 0 to 2, the area under the parabola for x between 0 and 2 is 8/3. Okay, so this is hard, not because it's intrinsically hard, but it's very new. It's completely different from the sorts of algebraic operations we've done in the course up to this point. And that's because the integral and the derivative are very different. So the derivative you get by a certain limiting process. You take the limit of the so-called difference quotients. But for the integral or the definite integral or the area under a curve, you take limits of Riemann sums. Any questions about this? I mean, this really is a lot to know. And on the departmental final, there is always one question about a Riemann sum. So you should learn what they are. Let's do another example. So this is in the book. This is example 5. we take the cubic curve. F of x equal x cubed. And we want to find what I'll write as the integral from 0 to 1 x cubed dx, which means the area under the curve for x between 0 and 1. So this curve looks like this. Y equal x cubed. So if you divide the interval up into n pieces, each piece will have length 1 over n. And if we take, for example, the right-hand endpoint of each interval, so xi minus 1 xi, that interval, that's the interval from I minus 1 over n to I over n. And if we choose the point ci to be the right-hand endpoint, I over n, then the Riemann sum, which is summation I goes from 1 up to n, f of c sub I delta x, that summation I goes from 1 to n, c sub I cubed, that's I over n cubed, times delta x, which is 1 over n. That's the Riemann sum. I can factor out the n's. I have n cubed times n. This is 1 over n to the 4th. Summation I goes from 1 to n, I cubed. But this is just the sum of the first n cubes. And I wrote down what that's equal to. That's equal to n times n plus 1 over 2 all squared. So what we get is, in the denominator, I have n to the 4th, and 2 squared is 4, and n times n plus 1 squared is n squared times n squared plus 2n plus 1. So n squared times n squared is n to the 4th, that's 1 over 4, plus 2n cubed over 4n to the 4th is 1 over 4n, and n squared over 4n to the 4th is, 2n cubed over 4n to the 4th, this is a 2, and n squared over this is 1 over 4n squared. Oh, sorry. Yeah, that's what it is. And the limit of this as n goes to infinity, these go to 0, is 1/4. So 1/4 is the integral from 0 to 1 of x cubed dx, or the area under the curve. So the general definition of a Riemann sum is as follows. you have the interval from A to B, and we divide it up into n pieces, not necessarily of equal length, so that A equal x0, x1, x2, x3, x4, and so forth, x sub n minus 1, and b is equal to x sub n. And in each interval from xi minus 1 to xi, you choose any number c sub I, so let ci be some number between xi minus 1 and xi. This is just what we did a moment ago, but without requiring that the endpoints of this interval, of these subintervals, be equally spaced. And the Riemann sum is summation, I goes from 1 to n, the value of the function at the point ci times what I'll call, well, times xi minus x sub I minus 1, the length of the subinterval, which we usually abbreviate by delta xi. That's xi minus 1. So this is summation f of ci delta xi. I goes from 1 up to n. That's what is called a Riemann sum. And it is sometimes called the norm of the partition. The partition is the set of n points is simply the maximum value of all these lengths. I'm doing this just because I have to follow the syllabus in the text, and this is really a background for what you need to know if you go beyond calculus 1 and 2. And the more general definition of the definite integral of a function is the integral from a to b of f of x dx is the limit, and you take the limit over all possible Riemann sums, f of ci delta xi, I goes from 1 up to n, where the norm or the width of the partition goes to 0. So if you let, for example, the delta xi's be equal to the length of the interval divided by n, this is automatically satisfied. And the big theorem is that this limit exists if the function f of x is simply continuous on the interval from a to b. And so this, if you like, is the formal definition of the definite integral. And the important thing for us is, well, there's several important things, but one important thing is that for a non-negative function, this tells us the area under the curve. So again, this is just to repeat. If f of x is greater than or equal to 0, then the integral from a to b, f of x dx, is the area under the curve y equals f of x for x between a and b. In fact, once you know that, you can calculate some integrals just by using geometry. So here's an integral that would be very hard to do directly. Suppose we take the curve y equals 4 minus x squared. Well, sorry. 4x minus x squared. No, that's a good problem, but that's too hard for us right now. Suppose we take y equals the square root of 4 minus x squared, and we want to find the integral. So this is only defined when 4 minus x squared is greater than or equal to 0, which means x squared is less than or equal to 4, which means x has to be between minus 2 and 2. So suppose I wanted to integrate this function from minus 2 to 2. What is this integral? Well, so we have to be a little bit sneaky, if you like. Suppose I let y equal the square root of 4 minus x squared. That means that y squared is 4 minus x squared, which means x squared plus y squared equals 4. And this is the equation of a circle of radius 2 with center at the origin. And if I take square root, that always means the non-negative square root. So this is the curve, minus 2 to 2. This is just, the graph is this semicircle. So this integral is the area of the semicircle, which is half the area of the circle. Right? Two semicircles make a circle. What's the area of a circle of radius 2? Pi r squared, 2 squared. That's 4 pi over 2, or 2 pi. So the area of the semicircle is 2 pi, and we could do the integral, minus 2 to 2, square root of 4 minus x squared dx equals 2 pi. We could do that because we recognize this as being the equation of a circle. Now I'm going to write down some simple properties of the integral, which you will use all the time. So this is properties of the definite integral. So the first is the following. If you take the integral from a to b of a function f of x dx, but you multiply f by k, you can take the k outside the integral. If you take the function f of x plus g of x, or f of x minus g of x, the integral from a to b of the sum of difference of two functions is the sum of or difference of their integrals. If you take an interval from a to b and you divide it into two parts, so you have a to c and c to b, the integral from a to b of f of x dx is the integral from a to c of f of x dx plus the integral from c to b of f of x dx. If your function is non-negative, you can see this in terms of area very easily. So here is A and here is B. The integral from A to B, that's the area under the curve. Suppose I take a point C. This is the area from A to C. This is the area from C to B. And what this says is this area plus this area is the total area. So if you think of this geometrically, it's very simple. One other property is the following. If you take the integral from A to A of f of x dx, that's always 0. Because it's like a vertical line has no area. And if you take the integral backwards from B to A, if you like, this is a definition. This is minus the integral from A to B. So if you reverse the upper and lower limits of integration, the sign changes. The integral from B to A is minus the integral from A to B. And there are 2 inequalities concerning integrals. If f of x is greater than or equal to 0 for x between A and B, then the integral from A to B of f of x dx is greater than or equal to 0. And if you have a function f of x less than or equal to g of x for x between A and B, then the integral from A to B of f of x dx is less than our integral of the integral from A to B of g of x dx. Okay. So we just covered in the book, chapter 5, sections 2 and 3. So there really is a lot here to learn. And you need to spend, I think, a fair amount of time studying the text and working on the problems. We have 2 more lectures on integration. On Wednesday, I will state and prove the fundamental theorem of calculus. So you know it's important because it's called the fundamental theorem. And on Monday next week, I will, the lesson concerns one method for computing integrals, which is called the method of substitution. So I'll talk about that. And then Wednesday of next week is the last class. And then we will go over the review, the practice exam. Oh, wow. All right. So we did a lot today. Are there questions about any of this? So I would encourage you to do as many homework problems as you can today and tomorrow, so that Wednesday morning in class, you can ask me to go over questions that you found complicated, perhaps. Okay. All right, well, if there are no questions, we will quit for the day. Be back on Wednesday. All right. Bye, everyone.